All right, we're back to talk more about standing waves. Instead of looking at standing waves on a string this time, now we're going to look at standing waves that are set up in a column of air. So this is very similar, or this is exactly how a musical instrument operates. What happens for most wind instruments, at least, obviously we're talking about wind instruments here, like woodwinds and brass instruments, is you have air chambers in these instruments in which these standing waves are set up. Air chambers and instruments help set up standing waves. Once the wave gets set up in that particular chamber, then the chamber, because it contains that wave, will start to resonate. Okay, so the chamber itself will start to vibrate, and that is what produces certain frequencies and tones. So the shape of these instruments is very, very important. The first example that we're going to look at are sound waves in a tube with two different open ends. Okay? An open end here, if you imagine you just have a tube, it's open on both ends, it's not capped on either end, so air is free to flow out both sides of this tube. These open ends, if air particles can move, okay, if air particles can move at either of these ends, these are like movable boundaries, because remember, sound waves work by oscillating air particles around. If the air particles at both ends can move, then those must be movable boundaries. And as we saw when we looked at boundaries, movable boundaries are where antinodes are located. So we have antinodes located at the ends. So we're going to draw a series, just like we did last time, of pictures of these sorts of tubes. You have to bear with me on the pictures because they're not going to be very pretty. Okay. All right. Yeah, that should be good. Okay. So we have a tube of length L. It is open at both ends. And we know that we want to have antinodes at the ends. So remember, an antinode, when we're drawing waves, is where there's like a big loop, okay? It's where there's maximum potential displacement for the particles. And I am going to make a point right now. We know that sound waves are longitudinal waves. However, it's kind of tough to draw longitudinal waves and sound waves in this sense, so you're going to have to forgive me. I'm actually going to draw them as transverse waves, even though that's not really what's happening here. So, like we did last time, we start by asking ourselves, okay, if we know we have to have antinodes at the two boundaries, what is the simplest standing wave to set up? And the answer would look something like this, and it doesn't really look like much of a wave to you, possibly. Remember that we're not these things aren't happening at the same time. The dotted line is one kind of snapshot of where the wave is. The solid line is another. But what we're seeing here is we have a standing wave that gets set up with an antinode here and an antinode here. Now, as far as the wavelength goes, how much of a wavelength is contained within this length L? You might be like, this doesn't look like a wave at all. But if you think about it, if this solid line, representing part of the wave, starts up here and ends up at the lowest point, so it goes from highest to lowest, that's half of a wavelength. So in this example, L, the length of the tube, is equal to lambda over 2. Okay? Now, that's not the only standing wave that we could set up. We could have another example, a tube of the same length, same dimensions, and we could have a standing, again, we have to have antinodes at both ends because we're dealing with open-ended tubes here, and that the open ends have antinodes located at them. We could also have something like this. Okay, This is another tube in which there is a standing wave. Notice this time that the standing wave is equal to the wavelength of the wave is equal to the length of the tube. And remember what we did last time? We tried to find the pattern, and we tried to make it so that all of these lengths were given in terms of the wavelength, some multiple of the wavelength over 2. So this could really be written as 2 lambda over 2. And again, the reason we're doing this is because we're trying to develop the pattern here. We could have, as you saw last time, an infinite number of different standing wave patterns, okay? The key is that they all have to be multiples of a half wavelength. If this is 1 lambda over 2, we could also fit 2 lambda over 2, 3 lambda over 2, 4 lambda over 2, and I'll draw those in just a second. But there's an infinite number as we keep reducing this wavelength. As we keep reducing this wavelength, we keep getting higher and higher frequencies that could be generated. And again, the reason that it has to be a certain number of half wavelengths in here is because we have these boundary conditions. Those are the most important parts. We have conditions that say at the open end that needs to be an antinode. At this open end there needs to be an antinode. If they are not, then the standing wave just won't be set up. There won't be any resonance. It won't. You won't hear any pitch. Okay, if you tried to have a wave go through here that didn't line up so that it had antinodes here and here, it wasn't the right length, you wouldn't hear this resonance. In any case, let's continue on with drawing our waves. For this one, we're going to have something approximately, let's see, this. Okay. It does get a little tricky to draw them after a while. Okay. So we have a standing wave that's set up, again, antinodes at both ends, and we have a certain number of waves trapped in here. Matter of fact, how many waves do we have? Let's see. Here's one full wave, and then it goes from top back down to the bottom. That is 1.5 wavelengths, so L is equal to 3 lambda over 2. And we'll do one more example. Where now we have 2 full wavelengths contained. Notice how, as we fit more wavelengths in the tube, each time the wavelength itself has to become smaller. Okay, so here L is equal to, the length of the tube is equal, I keep doing that, is equal to 2 lambda, or if we're going with our pattern, 4 lambda over 2. So again, notice that we have, the pattern seems to be multiples of a half wavelength. 1 times lambda over 2, 2 times lambda over 2, 3 times lambda over 2, 4 times lambda over 2. That 1, 2, 3, 4, what does that correspond to? Does it correspond to anything in the picture? If you look carefully, you'll notice that the number, this coefficient out in front of the half wavelength is the number of nodes. Here's 1 node, here's 2 nodes, 3 nodes, and 4 nodes. So here, the n value is equal to the number of nodes. So we could write the length in terms of the wavelength as this, L equals n lambda over 2. And something a little bit more useful and probably makes a little bit more sense is that the wavelengths that will work are must be equal to 2L divided by n. Okay, where n being the number of nodes, 2L being twice the length of the tube. So the possible wavelengths that will work must be equal to 2L divided by some number n, where n is 1, 2, 3, 4, etc., etc. Just like last time, we know that V is equal to frequency times the wavelength. To solve for the frequency, we know that it is equal to the velocity divided by lambda, the wavelength. I can substitute in for lambda so that I have V over 2L over n, where 2L over n is in the denominator. And finally, by multiplying by the reciprocal of the denominator, I end up with this familiar equation. The frequency that will be produced by different waves in a particular tube, the frequency is equal to n times v over 2L, for n equals 1, 2, 3, 4, dot, dot, dot. In other words, this formula is the same as for a string. The frequencies that will create standing waves are as follows. It's based on what mode of standing wave you want to set up. One with 1 node, 2 nodes, 3 nodes, 4 nodes. The speed of the waves in the air in the column, and the length of the tube. So really, you can't really do much to change the speed other than, I guess, change the temperature. What you're really dealing with here are the lengths. Okay, what you're really dealing with here are how can we create a tube of a certain length that will create the note, the pitch, the frequency that we want, and what type of oscillation, what mode of oscillation will we be setting up in here? Will it be the n equals 1 standing wave? Will it be the n equals 2 standing wave? What will it be? By the way, I'll label these now. This is n equals 1. This is n equals 2. This is n equals 3. And this is n equals 4. And again, these also have names like we talked about last time. N equals 1 is the fundamental frequency. This is the lowest frequency because it's the biggest wavelength that will produce a pitch, also known as the first harmonic. So in other words, n equals 1, and it kind of makes sense if you look at the equation, n equals 1 will give you the lowest frequency that any particular tube with a certain length and with speed of sound in air at a certain level, the n equals 1 standing wave will give you the lowest possible frequency. N equals 2 is known as the second harmonic, or the first overtone. Here's the third harmonic, second overtone, and here is the fourth harmonic, third overtone. Okay, so again, very, very similar to waves on a string. One of the nice things about this that I'll point out now is that if you know the length, if you know the length of a tube, if you know the speed of sound in air, and you know one of the and you can find one of the frequencies, then what you can actually do is you can work backwards by plugging in, okay, I know the length, I know the speed, I know the frequency. You can figure out what type of standing wave is in there, what mode, if it's n equals 1, 2, 3, 4, etc. And then you can work out all of the other frequencies at which this tube will oscillate. So that's kind of neat. If you know one frequency, the speed, and the length, you can determine which harmonic it is, and you can find the others, which is neat. I do want to make one point that I just thought of in terms of the speed. Sometimes, if you're in band, you might know this. If it's very, very hot or very, very cold, your instrument, it will be out of tune, more so than it normally is. And the reason for that is the temperature affects the speed of sound in air. So while the tube might be the perfect length for a certain temperature, if we change that temperature, that's going to change the speed in air. That's going to shift the frequency. So that's why very, very cold or very, very hot instruments often sound kind of out of tune, why we do a warm-up in the first place. Okay? So again, with sound waves in a tube with two open ends, what we're dealing with is we're trying to find the frequencies for sound waves that could be put into this tube and cause resonance, cause the tube to vibrate itself, cause it to produce this pitch. There are only certain frequencies that work. These frequencies correspond to there being an integer number of half wavelengths contained in the tube, because that meets the boundary conditions. The boundaries have to be 2 antinodes. It depends also on the speed of sound in air. It depends on the length of the tube. Okay? Again, we're going to get lots of practice with this. I know it's a lot of information right now. You're kind of like, well, why is this important? We'll do some demonstrations in class with this, and we will see why this might be important. When we come back for our last video, we'll talk about sound waves with one open and one closed end.